A very good evening to everyone. All of you, welcome to the fifth day of ATAL sponsored online 6-day faculty development program on Outlook on best practices and strategies for chip design implementation from industry perspective. Today, I am very honored to introduce our speaker. Our speaker is Sri T. Sai Krishna Garu. He completed his master's in VLSI system design and completed his BTech in ECE in JNTU Kakinada. Now, he is working as a lead engineer in Post Global Visakhapatnam. He is having 4 years of experience in uh, design for testability. Now, I would like to hand over this session to Sri T. Harisai Krishna Garu.
Hi, all. Good evening. Thank you.
Good evening,
sir. Am I audible? Yes.
Yes, sir. You are clear.
Yeah. Okay. Welcome to this lecture in the faculty development program. So basically, so you got the introduction right about me. So without wasting any time, let's just move into the main topic. So today our topic will be on design for testability, as is mentioned. Sir, your name?
My name is Venkatesh.
Venkatesh Garu. Okay, it is seeming as Krishna. Okay, that's no issue. Hi, Venkatesh Garu. Okay, thank you for allowing me to speak. And let me present my screen. Okay, is my screen visible?
Yes, sir. It is visible.
Yeah. Okay, so forget about this PPT, but I just prepared this PPT just to present in this FDP program. But beyond this PPT, I was willing to interested in explaining some real-time applications which is closely related to DFT. So may I know from any one of these audience, where does DFT lie in the entire VLSI design flow? I mean, I think all of are well positioned. I think most of you are elder than me, I think. So sorry for that, but that is true. But so let me know from you all audience. Give me some quick insights regarding design for testability. Where does it lie in the entire VLSI design flow or the chip design flow? What we learn from our lectures in the textbooks. I just want to know from the audience, any one of us. You can speak. Hello. You are able to speak, right? I think most of you can unmute. Speak. Hello. Hello.
Sir, you mean textbook, sir?
Yes. Hi, Rashid. So I just want to know, where does the DFT lie in our curriculum as we study in any lectures or any part of the textbooks? I just want to know some quick insights regarding this DFT topic.
Yeah, I'm not sure, sir.
Whether it is, I'll just give us some quick hints, whether it belongs to back end or front end, something like
Good
that.
evening, sir. Good evening, sir. This is Devi Pradeep. Yes, sir.
Good evening, Devi Pradeep, sir.
Yes, sir. Actually, when we go for digital IC design, whether it may be a semi-custom or you can go for any programmable logic ICs, we want to test each and every part, whether it has to work for all input combinations or them. For that, we are suggesting some methods like scan-based built-in self-test, which includes all test methodologies, all test cases, so that once the testing is done, then only product of the IC will comes out, sir. Generally, this is the one way only. We have to go for a number of ways, either test vector generation and all the things, sir. Yes, sir.
Okay, I mean to ask whether I think you are all well aware of this RTL to GDS flow. I mean the basic VLSI design flow, which is a fundamental step for the chip design in the industry as well as what we study in the books. So I just want to know where does the TFT lies in this entire design flow, whether it belongs to backend or front end.
Front end,
It's
front end, front end.
front end. Okay.
Front
Most
end.
of you
In
say
logical
okay.
verification, function of the IC and timing verification. In our end, we should go for n numbers way. One case is front end, which lies in the logical verification and product of IC.
Okay, but
It is there in back end, sir. After PD,
yes.
they will add some flip flops and boxes for checking
Okay.
checking easy.
Okay, let me explain. But it is a case of neither nor because see if the entire RTL to GDS flow is mandatory for the chip design, but most of the people doesn't know that without DFT we can still tape out the design. DFT is only mandatory when we go to mass production only. Please remember this word, mass production. When a organization or any MNC goes for mass production, then if and only if, then only the DFT comes into action. Until and unless DFT doesn't takes place, because they can't afford extra resource cost and all. So that is the reason DFT is an optional for RTL to GDS flow. Without DFT also, we still tape out the designs. We can go to fabrication. We can test. We can go to fab, but we can't test. The main motto of the DFT is to test the design.
Batch processing.
After the fabrication.
Okay.
Yes. So, and remember, DFT only is intended to test the manufacturing defects, but not check the functionality. So, in order to check the functionality, we already have separate domain called functional verification, and we have some test vectors from functional team in order to test the design functionality. So most of the people will have a assumption that DFT is meant to test the functionality, but not. But DFT, trust me, DFT indirectly tests the functionality. Until and unless the logic is correct, we can't simulate the design. Because we DFT people usually simulate the test vectors after completion of scan insertion, what you have mentioned just a few words ago. So we do scan insertion, we do perform embed, we do sorry, this is the ATPG. What the method needed for a pattern generation, what we call as test vectors. And another topic is the ATA testing, the main motto behind the DFT. I was going to explain this as well because I have experience of the ATA testing in the span of these 4 years only. It's a very unfortunate thing for me to experience this kind of scenario because if you go to industry, any other organization, people who are less experienced, like 2 to 3 years, won't get a chance of meeting the AT experts because they might not have a contact, because AT always expects a minimum of 10+ years experience candidates to involve this kind of technology. I mean the AT debug. Okay, the main motto of DFT lies here, the ATA testing. So without DFT, we can still tape out the design, remember, but we can't go for mass production. If the client goes for mass production without DFT, they will face a huge loss in their production cost as well, because the silicon itself takes a much more cost. We have some in the world, like we have some popular foundries like TSMC, MMIC, and Global Foundries, and Intel has its own foundry. These are the key players in the industry, in the semiconductor industry. And the TSMC almost occupies about 65% of global market by today. So that's the thing about the foundries and other. So this is the basic goal of DFT, what we have discussed till now. The main goal of the DFT is to test the design. I mean, the test the die. The fabricated design is called a die, and we will have a multiple dies on a single wafer. Please remember, the wafer consists of multiple dies. A wafer itself is silicon. I think you're all aware of that wafer, and right? I think you might heard of this terminology in the ATAL to GDS flow. I was not sure. You people need to tell me regarding this. Whether you have heard about this die wafer, and there are some terminologies like etching, lithography, masking. This all comes under a fabrication processor. This is entirely a separate topic which is not related to RTL to GDS flow, but it is related to chip, the basic idea of the real-time application to chip. So here we have this is the basic flow, what you see in the textbooks or any other online material, the RTL to GDS. But the real flow like this. Let me draw. Let me use paint. Okay. So the basic, sorry, the idea we put into RTL coding, where it depends on chip specifications, and then we go to GDS. I mean the layout. This is the final output that goes to foundry. Okay. After going to foundry, it takes a critical steps like whether I don't know whether Venkatesh, whether do you have any idea? Do you people heard about this foundry manufacturing techniques in the previous classes?
It means the IC fabrication
Yes,
techniques.
yes, fabrication part. Yes, yes. It
Yes, sir.
involves series of steps. Yes, yes. Okay. Basically, in the introduction class, we might heard. I think someone should explain this. The basic techniques beyond a manufacturing process, where it takes place at the foundry, and foundry to chip. So, and when it comes to testing, right? A minute. So when it comes to testing, there will be two types of testing. One will be on the die. That means unpackaged design. I mean unpackaged unit. We call it as die. It is a fabricated one. Another is packaged testing. So the font is somewhat big. So right at the packaging, we do test the design. Sorry, we do test the dies again at the packaging level. These are the two kinds of testing we do. From my experience, the first level testing will be performed on the die. I mean, the manufactured product is called a die. The die looks like, let me show one picture. Yes, present. Meanwhile, so this is how, is my screen visible, right? Hello?
Yes, sir.
I was presenting a picture. Is that being present? I think I have shared.
Yes, sir. It is in Foundry, I think.
Yes, yes. This is the ATE lab. We call it as an ATE lab. So generally, the testing takes place in sensitive temperature conditions, as you know. This is a wafer, and wafer consists of dies like this. I will just draw. Okay. Before I start, This is how a die looks like. The entire unit is called a wafer, and we will be having dies on it. I mean, replica of a single design. When we tape out a single design, it will be a replica of multiple times like this. Each unit is called a die. So in order to test the defects present on this silicon, consider this is a silicon wafer. We call it as wafer. The terminology is called wafer. And this is a die. Okay. In order to test the manufacturing defects, I mean the defects which are present on the silicon, that in turn malfunctions the entire unit. A single defect sometimes a single defect can cause the entire chip to fail. Is that right? Am I correct or not? Hello, please respond back.
Yes, sir.
Hello. Yes. Okay. Sorry. Let me consider a single die like this. So let us assume this is a single die. So if this single die falls here at this position, we might observe, we see there is no, this is a plane in texture currently. Let us assume there is no manufacturing defect right here. But when we go like this, here and here and here, let us consider these black dots as a defect, a manufacturing defect, we call it as. So in order to test these manufacturing defects, we use DFT techniques. So what was that one DFT technique? What was that one DFT output that is able to test is like our pattern. We call it as pattern. We call it as pattern. So the overall DFT output at the time of tape out or hand out, at the time of tape out in the sense, do you have an idea about tape out, right? People who are here in this meet. The
Yes,
term tape out. Yes. See, fulfilling all the complexities or responsibilities from each and every domain, right from RTL to GDS, is called a tape out processor. So that is the end of the RTL to GDS flow. Okay, the tape out in the industry we call it as tape out, or like sign off. We call it as sign off. So after the tape out, people from different domains, like you take it as PD, PV, or DV, digital verification, or a functional verification team. Every team, they will be handing over their outputs to the client. So that scenario is called as tape out. So from DFT perspective, what we hand over is called pattern. So this is the final output that goes to client, but this does not helpful in manufacturing. What is useful is the layout and some other IP files, IPs, and some design related information from the designer. This is what goes to foundry, like foundries like TSMC or MMIC. They collect information for the fabrication process. So what was the pattern about? As we discussed now, the pattern is all about ATE test, where you can see this is how a lab look like. Sorry, this is from the I have downloaded somewhere from the Google, but let me show another pic. Not this. I think it stopped somewhere. I think it should be down here somewhere. Okay, so for testing procedure, okay, listen to me. Okay, for testing procedure, there will be a separate equipment called ATE, automated testing equipment. We call it as. So engineers, ATE engineers who work on these scenario will collect the pattern. So soon after the fabrication, the people ask the DFT engineers, or the client asks DFT engineers to deliver the pattern. And right after the tape out also we give pattern, but see, there will be some delay in the pattern delivery sometimes, because we people sometimes compromise on the GLS results. See, if the tape out deadline is very near for us, we might compromise on the testing procedure. I will explain later in this lecture. Now let's go to goal. Okay, so this is how. So this is the input what we talked about. This is the test pattern that is being the input for the AD and the fabricated die, and the dies will be each die. Sorry, the entire wafer will be tested, not the single die, and the entire wafer will be tested in order to reduce the test. Die testing is very rare in cases of ATE test, but when you go for real-time ATE test, they always test for a wafer-based testing, because in a small amount of time, people do test the entire wafer and they collect information on a scale of full dies, and they will calculate the yield. So, and another most important aspect is the yield. Let's talk about yield now. Come on. Okay, just erased. Let me undo. So basically, wafer testing will be done like this. So this is consider this is a wafer. Let us consider this is a wafer. So when the AT people test the entire wafer, they will calculate the number of passing parts out of all the dies. This looks like the yield is related to number of passing parts by total number of parts present on the die and the wafer into 100%. So trust me, yield always matters. Yield always matters. This is closely related to market, time to market, or something related to their business. I will just explain how this is related to market. Before that, I just want to know from you guys regarding this terminology like original part, spare part. So most of us use electronics in our day-to-day life. So consider an example in our household appliance like television. If something goes wrong with the television, what do you guys first prefer? I will just give out the options. You can unmute and tell me. Hello. Hello.
Yes, sir.
Okay, you can go out and tell
First,
me.
we will go for repair.
Okay, repair, and then so if the repair doesn't work, what shall you do?
We will replace the parts.
So to replace the part, what part do you choose from this one? You can
Original part with spare part.
original part with spare part. So you're going to buy two parts at a time.
No, sir. If
Okay.
there is any problem in original part, we will replace it with a spare part.
spare part. So does the spare part is very similar to original part? In what aspects?
In functionality aspect.
Okay, but remember, spare part has no warranty or guarantee, right? Sometimes spare part has no warranty or guarantee. Is that true?
Yes, sir.
Why? Wha- See, this is where I was going. I was interested in explaining or trying to explain the real-time application. You people can think meanwhile. So I think many of the audience are present. I think it's 108. The count is 108. See, I will just give out a scenario, brief scenario. So consider I was the person who has bought some spare part for my television in my home. So I have replaced the entire motherboard with the low-cost spare part which was available in the nearby store. But the functionality has worked while it was assembled at the technician, and it has even worked for 3 months, 3 to 6 months. Let us assume. But the vendor says, "Sir, this is a part which might work for 3 months. We can give you a guarantee for the 3 months, and if anything goes wrong, we can replace, sir." So that is what he has said. But later upon using after 3 months, and the 5th month, I got to see the failure in the an entire unit. Consider it as television. So what do you think? What might go wrong in this scenario?
Maybe it is not compatible with all other different parts in the TV.
Okay, Venkatesh Garu, you are answering the entire questions. Let others speak. I think there are 108. It's okay you to speak, but there are audience in this meet. I think people who have spoke earlier or any other people can speak. So see, this is the main motto of the TFT that I was trying to explain. So explaining the concepts like scan, M-based, ATPZ doesn't feed you, doesn't account or doesn't facilitate this program. So what I was trying to explain is the basic, the most advanced topic like the real-time applications, what we engineers actually do. How does this correlation takes place? Okay, let me tell you. Okay, so is anyone going to answer so that I can wait or I can explain? Otherwise, I will explain. Venkatesh Garu, you can talk if you want to talk. I think I stopped you. I was stopping you from talking. You can talk, please.
Maybe the space part is not compatible with all other parts in that system, sir.
Okay, compatible. Okay, but see, when we go and buy a spare part, does spare part look alike like original part? Am I right? I think it might look alike.
Yes, sir.
Yes, I mean the direction of IOs. So when you consider a motherboard, when you compare the spare part and the original part, if you go from LHS to RHS, the connections in the outermost parts like resistors or analog bus connections, something like that, will be visible similar. Am I right?
Yes.
Yes. If you compare two birds, identical boards, sorry, the motherboard, from LHS to RHS, if you could see, the entire connections seems to be same. But what differs is the connections in depth varies. So what variation is that? It is manufacturing defect. It is some manufacturing defect. So you can ask me now, why does the part has manufacturing defect although the parts were tested right after the fab? You should have get a doubt like so. Hari, you have just said right after the tape out, right after the fab, the parts will be tested whether there were the passing parts or failing parts. So if the passing parts comes out from the testing area, why does a manufacturing defect part, something like spare part, comes into market? You may have this doubt, right? Isn't it true? I think someone should answer. Hello.
Yes, sir. Yes.
Yes. Okay. So the main focus is testing. So we do test multiple parts. Some will be our passing parts. Some will be of defective parts. So if the entire passing parts category 1, then where does this defective part goes? Do you think the vendor or like the client throws out after hello, am I audible? There was
Yes, sir.
Okay.
Yes, sir, you are
So,
audible.
yes. So there are two categories from the testing output. There are passing parts and there are defective parts. And in these defective parts, there are some more category like more critical more defective. Let us say it as more defective. These come under category 3. Let us assume this is category 2. And another is too much failing. I will differentiate these categories in detail. Okay, let us assume these are 4 categories. The first category is of passing part. That means the die has no manufacturing defect on it. Okay, and the rest of all are the defective parts, and they belongs to different categories. The cat 2 has some minute defects. This is like
Sir,
greater than category 2. I was not sharing my screen or what? Is my screen
is visible, ma'am.
Okay.
Yes, sir, now it is visible.
Okay. That's see. Let us assume these are the 4 categories. You can exclude the category 1 because it has passing parts. It has no manufacturing defect, and there are some other category parts out of the manufacturing time. Like I just said. Sorry. Consider this is as a die. So the parts which are passing has no manufacturing defects. I just explained in my previous slide. And some parts which has manufacturing defects like this.
Sir,
Yes, please.
how can we judge percentage defective with percentage, sir?
It is like this, ma'am. Just like this is the defective percentage, what we call as yield. In our industry terminology, what we call as yield. This is the
Okay,
formula to calculate the in order to differentiate the passing parts, and in order to differentiate the passing parts, we have the pattern. But in order to test the overall quality, I mean the overall passing criteria on the single vapor, we calculate this form. We calculate with this formula. And suppose consider this is a vapor.
Sir,
Sorry about the
sir, sorry.
yes.
Again,
Yes,
your
sir.
screen is not visible, sir.
What about
Ma'am,
rest of others?
screen visible out. Ma'am, SaaS screen is visible, ma'am. Maybe your
Okay,
side
okay.
some internet problem is.
Oh,
Okay,
okay, okay.
no
I will
issue.
check.
It is visible, ma'am.
Okay,
Okay,
let us
okay.
consider.
Thank you.
Okay. Just listen to me. Okay, if you need any assistance, you can contact me personally by after the end of this lecture. I can help you out. No issues. But let us continue with this lecture. And see, consider this is a vapor. If you consider this vapor, there are passing parts. Let us count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So out of what are the total number of parts here? 13, 1, 2, 3, 4, 4, 8, 12, 15. Let us say it was 18, the total number of parts. Out of 18, there were 13 parts got passing. So this belongs to this category. So the rest will be, sorry, the rest are 5. The rest will be shared by these categories. And depending upon a severity of the manufacturing defects, what foundry does is they will account with process called, okay, let me off this. They will account with process called binning. This is what the foundry does. Binning is like they will differentiate the defective parts into separate category based on the failing severity. So now you might understood the concept behind the original part and the spare part, right? I think most of you can get some conclusion regarding this, what I was trying to explain, the difference between the passing part and the defective part. Now, people in this meet has any idea about, so did you get any idea about this concept? Hello.
Yes, sir.
Yes.
Sir, if any defective parts are there, what you will do?
We will do the diagnosis. We will do the diagnosis. So this concept is called ATA diagnosis. What I have mentioned in my slides. This is a separate topic where actual DFT goal meets. So until and unless the parts gets failed, the foundry or client doesn't ask our engineers to do this procedure, the ATA diagnosis. And for ATE diagnosis, I should explain one thing. If anything goes wrong on the
Sir, excuse me, sir.
Yes, yes.
You will do diagnosis for category 3 also?
Yes, yes. Actually, we do diagnosis in order to differentiate these categories. Because foundry cannot categorize these parts into categories. until and unless we people perform diagnosis and give out the results. See, the testing will be performed like this. So they will consider, let us say, there are n vapors in a lot. So collection of vapors is called a lot. So let us say 6 out of 10 got passed. I was just writing the real-time scenario. Please try to understand. So 6 out of 10 vapors got passed. What does this mean is no dye on these 6 vapors has manufacturing defect. See, there are 10 vapors in a lot. So fab team has given a lot with ID. There will be a specific ID for this lot. Something like 1, 2, 3, 4 letters. Yes, please.
Sir, as we are testing dice here, so what type of testing setup actually we should have in real time, sir?
For real-time testing, it will be done from the AT end, ma'am. We don't have an access. Yes, the AT equipment, which is highly cost in terms of it was a very sensitive equipment. Actually, we in our country we don't have this facility right now.
Okay.
But very soon we will be having this facility. I hope it will be first initiated in Gujarat or Assam, Tanishika in coming years. But right now I can explain the AT testing procedure, but not the AT equipment. But I can draw a sample block diagram like thing where I can explain the procedure for AT test. So is that okay?
But whatever DFT process actually now industries are doing, in most of the companies, they'll use EDA tools, no? Any of the from any of the vendors, not
Yes,
through this AT equipment. Whatever you are saying, that also we
yes,
have. No?
Yes. We use EDA tools for only implementation, ma'am. The entire technique implementation of DFT techniques only, but not for AT test. Okay. Because we don't have a facility here in India to test dice, especially for AT. I mean the manufacturing defect index. Maybe AT people might use the EDA tool, but it was not closely related to DFT techniques. I mean, whatever the tools we use, basically you might heard of mental graphics tool.
Yes, sir.
Mental graphics, popular tools. We have Synopsys,
Cadence,
and Ultra, something like that.
Okay.
Ultra. There are some specific tools, but majorly these are the main 3 tools what we in industry use. I was familiar with all these 3 tools. I use these tools for one or the other aspect during my implementation, but not for AT testing. But I can have closely worked with AT engineers. So what AT does is I can show you with the sample block diagram here.
Okay. Sir, how can we differentiate the errors we get in DFT process and with the formal verification, sir?
Formal verification, okay. Formal verification is closely related to LEC.
Functional.
Yes.
No. General verification. Initial stages in the functional verification. No?
But functional verification is not a part of DFT. As I explained in the start of my lecture, DFT does not test the functionality of the design. The main intention is to test the manufacturing defects present on the silicon. So when you consider a silicon wafer like thing, just I have drawn. Sorry, I was bad at drawing, but consider a silicon. It was a symmetrical structure. I mean, it's a circular in structure with multiple dies, n number of dies. So when you take this silicon, it undergoes several steps until the die gets manufactured, like etching or lithography. We call it as masking, something like that.
Yes, sir. That I could
Yes.
understand. What I mean to
Yes.
say is, as you're saying, ATE equipment is not available in our country. So
Yes, yes.
whatever industries, the DFT, as far as DFT is concerned, just now you said the various CDA tools actually you are using. So
Yes.
what type of errors actually in the DFT step we can
Okay.
have when you do that testing
yes,
process?
Okay, during implementation.
Errors, I'm saying. Yeah,
Yes,
yeah. During
it's not the errors. We call it as DRCs, ma'am. Design rule checks.
design
We
rule
face
checks. Okay.
design rule checks. So basically, these are from A to Z. I think there will be some set of rules. A is for RAM rule, P for pitched, C for clock, T for data, E tends to extra rules, F tends to EDT finder rule. This is in terms of mental graphics, ma'am. Doesn't, I mean, the basic, when we implement a DFT technique with mental graphics too, these are the kind of DRCs we get, and it may varies with tool to tool. When you go to Synopsys, I mean the design compiler, DC shell we call it as, or Cadence
DC,
NCSym. Yes. So these DRC IDs may vary. Please remember, this is only in terms of test center. Okay. G we call it as general rules. In I we have ECL extraction rules. ECL tends to instrument connectivity language. It describes about the extra design we add in the existing design. So the main motto of the DFT is to add some extra design in the existing design, so that to make that circuit, to make the design testable. So this is the main principle behind the DFT that I forgot to explain in the first lecture. Very soon I got to. Was very intended to explain this major application, real-time application, because most of you are well educated, I think, in profession, right? So you're not it's not like a student seminar. So I just went through the real-time application because I do understand many people have no have no idea regarding where what really DFT does. What's the use of DFT in the entire VLSI design flow? So that is why I have come into this topic. But not to forget, the basic goal is to make the design testable. That is the basic fundamental funda. We call it as in our domain. And till semantics, we call it as another. J doesn't, with J there is no rule. K is for only EDT rule. This is entirely different from F. F finds for F tends to EDT finder, whereas E tends to only EDT rule. This varies, but explaining in depth in EDT finder and EDT can't be done in this lecture. Sorry to that, but we can only find these types of DRCs when you go through the implementation. Even if I explain, because basically there is no scope here to explain, because when we have a design or EDA tool, I can do so. There is no rule with L, M, N, and O. P is for procedural rule. There is a R. This is a core mapping rule, we call it as. S is for scannability check, scannability rule. T is for trace rule. Basically, we call it as scan chain tracing. If you heard about the scan chain in your books, I mean that in the any other material, we call it a scan chain. We have you doesn't have, we don't have any DRC with starting with U, but we have V, power aware rules. X is for X bounding rule, call it as small d. We don't have any rule that starts with Y and Z. These are some of the rules. I think I have covered most of the rules. If I go, let me check if I am missing anything. A, B, C, D, E, F, G, H, I, J. There is no J, K, L. There is no M and rule. Okay, and these are further subcategorized depending upon the type of violation, ma'am. Sorry, all of you, please listen. And these are some DRCs as, ma'am, what is your name? Your Miss
Leela, sir. Leela.
Leela. Hi, ma'am. Leela. So as Leela Gar asked, these are the basic DRCs, not the errors. Errors are again different, and we might face some errors as well. Errors in terms of setup. So there is one such scenario, not the scenario, it's a basic criteria you can see, like error, we might fall into errors when any of our input goes wrong. So we have different kinds of errors, like elaboration errors, we call it as. So if the DFT engineer tends to read the design in a Verilog format or any kind of system Verilog code format, if anything goes wrong in the entire code, we might end up in facing these elaboration errors. Incorrect inputs, invalid inputs, input files. We can say it as input files. Ma'am, this is the one which you have asked. Basically we find errors
Yes, sir. Yes, sir.
when our setup goes wrong. So let us consider a real-time implementation like scan. Basically, for scan, we should have a gate level netlist as input. Library files. ECL files. If insertion happened, so this is the basic criteria, man, for scan implementation. These are the basic inputs. So whenever if something goes wrong in the netlist, I mean some instantiations goes wrong in the Verilog code, we might end up in elaboration error. So this is what you have asked for. And when coming to implementation, I think I have come across to another topic. So what do you want me to finish first? This one or this? Your choice. It's audience choice. Okay. Hello. Hello.
Yes, sir.
Do you want me to finish this?
You are audible.
Yeah. Yes, I am audible. So, as Leela Gar asked, I have explained some errors and DRCs during implementation. She asked about what are all the errors do you face during implementation. So this is what I have. The info from my end. There are basically what we call in the industry as during our implementation using the EDA tools. This is that we call it as DRCs. It's the design rule check. So basically, you might be aware of this design rule check. So anything, any rule that violates the design criteria. So what design criteria is? Basically, our design basically consists of clock signals, resets, and data, if I'm not wrong. So if the connection goes wrong, or there might be any unconnected net or any unconnected wire in between the design, so the tool ends up in throwing some DRC. So user, please see there is some kind of DRCs that fall into one of these categories, stating that your clock propagation is not proper. You might fall under some category like DFT-C6. Or if the clock is related to memory kind of thing, you might fall under DFT-C9. And if there is a reset signal is not proper, you might fall under DFT-C9. These are some of the subcategories of DRCs in terms of C. Remember, in terms of C, these are related to clock. So when I'm a little bit fast, or do you want me to change my style, something like that? So many of you haven't been responding. Hello. Hello.
No, sir, you're in phase.
You're in phase. I'm in phase, right? Okay. So do you want me to continue with the implementation methodology, or do you want me to finish this testing procedure?
Which is important as per your expertise.
Okay.
That first finish.
Okay. The main motive is the test. That is what I want to explain all of you. The main motive or the real-time application where DFT falls. So that is what I want to go into explain. Not just say not just the PPT, because you guys might be aware of these concepts like structural testing, functional testing, or fault model, something like that. I have prepared this PPT for the namesake for this program, but beyond this, I want to explain the real-time scenarios. That's the main motive of this session. So you can get this info from any of the textbooks, if I'm not wrong, or any of the online lectures. But what I am trying is the real-time scenario where the DFT connects. The DFT connects the entire market, entire chip market. Okay. So let's come here. I think, ma'am, I have cleared your doubt or question, like something like that.
Yes, sir. Yes, sir. Thank you.
Yes,
Thank
I will continue, ma'am. There are
Sure.
many more to talk, but my motive is to understand the real-time perspective. So we have talked about different categories like passing and failing parts, right? So please observe this particular part here. I'll just use the board. See. Sorry, it was getting highlighted. I think, sorry, it was getting highlighted by. I was new to use this board. It's a drawing board. That was another one. It's okay. Okay, see this particular part which has more number of defects compared to others. Is that true?
Yes.
So when compared to our other parts which has defects, this has single defect. This has multiple defects. This has two defects each, and this has one defect. So they, depending upon these defect count, we categorize the failing criteria or the binning, what we call it as binning. Okay. See, the entire binning depends upon the ATE diagnosis again. So because the ATE engineer does not know how many defects are present on the each die, but the DFT engineer can know. Even ATE engineer can do the diagnosis if he is aware of the DFT technologies, because I see most of the experienced people who works for DFT or DFX in domain will shift to this ATE testing position in many of the MNCs. So that is where advantage where the ATE engineer can perform diagnosis by himself and he can measure the failing severity. So let us consider the entire silicon has this cost around something like Indian currency, we call it as 100K, something like that. Assume you had a budget of 100K in manufacturing one wafer by TSMC, which has a success rate of 90%. So currently the success rate from TSMC foundry is 90%. So why TSMC has occupied the overall global market by 65% is the reason because of its success rate. It guarantees that if a wafer is about to fabricated with some design unit, we will be having 90 passing parts out of 100. Assume there are 100 dies on a single wafer. The foundry guarantees there will be a definite parts of 90 out of 100, where other 10 will fall into defective category. This is what the success rate from the TSMC. When you give a budget of 100K or something like that, it varies depending upon the quality of the silicon. Again, the overall budget will be for a single wafer or entire lot will be different. So when I assume that when I consider a company like TechGaint, like Apple, so Apple do manufacture these series like A series and M series. A series will be used for the iPhones and all, and M series will be used for MacBooks. Consider Apple TechGaint has given a order for TSMC to manufacture different number of wafers. Considering it, let us consider an advanced A17 chip or something like that. That includes AI technology. So if the Apple gives a contract for TSMC like this, it gives a TSMC guarantee 90%, where out of 100 there will be definite passing of 90 or 80, something like that. Apple doesn't, a company doesn't care about some XYZ doesn't care about these passing parts, because AT or client doesn't question about the passing part. They always question about the failing part. And we DFT are not responsible. Remember this one point, because I have faced this scenario from the client which I have worked. Basically, I work for ADAS application, where you can see in the automobile the self-driving assistance system. So 1 year ago, I have faced this question from the client, like, see Hari, there are you have given us a pattern, the pattern which has got the timing GLS passed from my end, and when this pattern is tested on the fab, right after the fab, there were some failing patterns. They said the failing patterns. So this is the terminology itself is incorrect. So our pattern does not fail. Remember, there will be no terminology. There is no word like something like failing pattern. This is wrong. Okay. So I have corrected them, like it's not the pattern that is getting failed, it's the silicon that fails. If someone says you there were some failing patterns on the silicon, please do correct them. It's not the pattern that fails, it's the silicon that fails. So our motive is to test the silicon and the manufacturing defects present on it. See, I have given an example like this. There were some passing parts on the silicon. See, and all the design units are same, and all the design units lies on the single wafer. Isn't it correct? Any of you can respond?
Yes, sir.
Yes. So then why does silicon? Then why does the defects present on some dies, not on all the dies, is the question. So in order to test or in order to differentiate this kind of scenario, we have the pattern. We have this DFT technique. Did you guys understand the motive behind the DFT? Hello, everyone. Rest of the
Yes,
people.
sir. Understood.
Sorry. Yes. So this is the main motive. So you might ask, Hari, there are passing parts. Okay, you can easily get the passing parts and can be built on the actual system. So passing parts which are of category A, category 1, let us say, cat 1 will be goes to actual unit. Consider it as a TV appliance or something like that. The brand new TV appliance or mobile, something like that, or any electronic gadget. Then what does the failing part or defective part do? You can answer this question with ease now. Come on. Come on, audience, any of you can answer this question. Tell me. Should I repeat what I have said just now? Hello, people, audience in this meet.
Sir, maybe defective
Understood.
part, maybe like a spare part in future.
Yes, yes,
with the
correct.
minor modification.
Not future. The current trend is that, so you can see the reliability does matter between the passing part and the defective parts. So when you buy
Yeah,
an
yeah.
TV or mobile, the what you buy is the actual unit will have a more warranty or guarantee from the company, but the same warranty or guarantee does not company does not guarantee for the spare part.
Spare parts, yes.
Yes, so this is where the DFT plays a crucial role in the market. This is what I want to explain. The main motive behind DFT technique, I mean the DFT domain in the VLSI system design, or the VLSI, entire VLSI design flow. So this is what the DFT does, what DFT engineers strive to do all the day. So this is the main motive. So consider, some XYZ company like Apple or Samsung or something like that. If they manufacture n number of units considering the different wafers, so what would they what would happen if they consider only 90 passing parts and the rest 10? What do you think they will do? Do they easily throw out, or do they easily crash them? Something like that. They won't. They can't do, because they invest some millions or billions of dollars in the current the current electronic gadget market. Am I right? They make use of every part that was manufactured from the foundry in one way or the other, like a spare part or the original actual part. This is what companies do. So what about these part? And if you could see the part with more number of defects will fall into another category, trash. The part with more number of defects will be trashed, will be simply thrown. Okay. I think audience in this meet are aware of this now. Hello.
Yes, sir.
Yes. So this is what I was trying to explain. The main motive behind the DFT and the testing methodology. So why people or why industries do opt for DFT is the reason is this. What you see in the textbooks or what you heard from the other engineers or the industrial experts in terms of implementation. End of the day, what matters is the yield and the categorization of passing parts and the defective parts. Clients, trust me, clients do not care about this. How hard do you work? They always focus on these strategies, the time to market and the other PPA factors and all. But implementation wise, we need to focus. We need to fulfill each and every technique of the entire DFT implementation, because if something goes wrong and something like improper fixing of any of the DRCs, may not fulfill the DFT implementation technique. Trust me. Now let us discuss another topic. Okay.
Sir, excuse me, sir.
Yes.
How much yield will be acceptable for spare parts, sir?
Venkatesh Garu, there is no yield percentage for the spare parts. It's yield will be calculated on entire lot or entire wafer. Actually, it will be on the lot, not the wafer, because lot consists of n number of wafers. Suppose you think some company XYZ has given an order for TSMC kind of foundry. They do order like some 1 or 2 lots, I think, for initial test. For initial testing, they will do order 1 or 2 lots. Based upon the testing of these 2 lots, they will ask foundry to further manufacture the different remaining parts. It's not about see, if something goes wrong on the silicon or the foundry end, we can't face the damage that has happened for the more number of parts. So that is why the company, the client or company, something like just like I said, XYZ company has ordered some n number of lots to a foundry like TSMC. That XYZ company doesn't risk in manufacturing more number of parts. They do because as they given the order for TSMC, TSMC guarantees some success rate like 90% based upon their quality of the silicon. So this quality of the silicon and the guarantee should be fulfilled by the testing team. The foundry and the testing team may not be same or may not be different. Sometimes the foundry and testing will be taken place at one place, and foundry will be different from the testing team as well. From my experience, the foundry is TSMC. Like I have worked for 48 and 28 nanometer, and testing will be done by other companies. Like just like service-based companies in India, there are testing companies like in China, like in countries like China and Japan. They do take these wafers, and they will consider these wafers for ATE testing. What earlier ma'am has asked. So how ATE testing takes place. So there will be a separate company, ma'am. They will have an equipment. They will have their own EDA tools. They will test initial lots of 2 or 3. Depending upon the results of these 2 or 3 lots, the client asks foundry to further manufacture the remaining parts. So if the 2 or 3 lots guarantees this success rate, client believes that foundry has satisfied their goals, like success rate or something like that. So depending upon the yield, when Venkatesh Gar asked about the yield, so yield will be calculated per lot. So for suppose, consider there is a lot consisting of 10 wafers. Out of 10 wafers, for each wafer there will be they will calculate the yield. For entire lot, they will be calculated the cumulative yield of each wafer. I mean, so consider this is a single wafer. There are 10 wafers like this in a single lot. For each wafer, they will calculate the yield just like this, with this percentage. Depending upon this percentage, they will calculate the entire yield for one single lot. Are you getting my point?
Yes, sir.
Yes, okay. This is how yield is calculated. But see, for spare parts, they don't. They might not go for yield calculation because, see, foundry already guarantees you 90% success rate for each silicon wafer. This is the success rate for each silicon wafer, not the lot. Okay. So if there are defective parts, they will be categorized into separate scenario. Like this is called binning. We have talked about. This process is called binning. That the categorizing the defective parts from the actual passing parts is called binning. In binning, we don't have any passing part. Bin is like the term itself says bin means the defective parts will be categorized into different categories based on the failure severity. Okay. See, there are end defects on each and every failing part. Here 1 and here 2, and there are multiple defects, and these will be categorized. And for this categorization, ATE or TFT engineer need to perform ATE diagnosis. That is what the procedure we call it as ATE diagnosis.
Okay, sir.
Okay. Is there anything from your end that you want to know, or do you want me to continue like PPT wise or something like that? Like others asked, there were errors during implementation. What kind of errors do you face, sir? So I have explained about errors in DRCs from my end. And is there anything you want to correlate theoretical with the practical criteria? You can ask. Any of the audience, any of you from the audience.
Sir, actually, AT is used for fabrication related errors, right?
Yes, what we call as manufacturing defects.
Okay, so ATE people will work for foundry, or they will work for some functional design company?
See, ATE will be of two types. They will do the functional test. They will do the functional test as well, and they will do the manufacturing test also. See, this test is entirely different from this. So I should differentiate these tests in some few lines. See, functional test is directly related to your testing logic. I mean, the logic present in the design. So there are some cases in terms of these tests.
Is it validation?
Yes, you can term it as validation. Even we DFT people call it as validation, but these what are the pattern we validate does not account for functionality test. We do account for only manufacturing test. The DFT pattern only tends to manufacturing test. As I said earlier, the DFT is not intended to test the design. I mean the functionality test for functionality testing. It is there for the manufacturing testing. But DFT, remember, DFT indirectly test the functionality of the design. But the main motive is the manufacturing test only. See, until and unless if the functionality is incorrect, you might end up in failures during simulation only. You can't proceed further. Even if functionality test fails at some part of the VLSI design flow or during your chip tape-out process, there might be some RTL update from the top level team, I mean the front-end team. But these functionality doesn't matter for DFT. The main motive of the DFT is to make the circuit testable. So in order to make that circuit testable, we have a mantra called controllability. I think you heard about controllability and observability. I think most of you heard about controllability and observability in terms of in your textbooks or lectures or something like that. So this is the main principle we follow as a DFT engineer. We make that circuit testable. We take the control over the entire design, the entire digital design in our hands, so that every part of every node or every pin will be in our hands. So let me draw a design and explain. I'll do the same. Okay. So consider this is our entire design. The name is TikTok. So this is our entire design. We will be having separate hierarchies inside the design, and each hierarchy will tend to functionality depending upon the chip specification. And further, these hierarchies are further classified into instances like this. And in between, there will be your logic. See, don't think the design will be as simpler as this, as I was showing. Consider this is an example. So on the top of the design, we will be having some ports. There will be n number of ports. Consider some ports might come from analog design. See, this is not the entire chip. I was talking about only digital design, only the digital part, not the chip level. So chip level will be further classified as analog plus digital. The entire analog digital will comes into action. Consider this is the digital, and this is our, we call it as pin mux. This will be the pin mux logic. And for DFT people, or for our DFT, in order to implement this DFT, we will be having some dedicated pins. Consider there are like 15 pins will be given to DFT. And we call it as scan mode, scan enable. We have clock and compression update, which is used for EDT. And we will be having JTAG pins. So if the IO needs to be tested, we will be having JTAG lock, JTAG T reset, JTAG test mode select pin, TDI pin, JTAG TDI, this is the input, and TDO pin. This is in terms of JTAG. And we'll be having scan pins. And trust me, the entire design will be controlled under these 15 or 12 to 15 pins. And I forgot scan it. And the count may vary, some 1, 2, 3, depending upon the complexity of the design. These may vary. Because when you use the compression techniques for something like EDT, we will be having like more number of pins in order to reduce the test time on ATE. So when again, when it comes to these pin criteria, we use EDT techniques. So I forgot to mention this point regarding in terms of test. So test time. So whenever testing takes place, you might be aware of these nanometer technologies like N6nm, 3nm, or something like that. Consider there is a the instance count or cell count is like around 5 million. Design instance count. Okay. This is the question for our audience here in this mid. Consider there is a 5 million design instance count. Then what will be the cell count? Can you even estimate the cell count in terms of fingers on the finger count? So it will be more, right? Consider as 1 million, not 5 million. Tell me, there are 1 million design instance count in your entire design like this. Then what will be the cell count? You can estimate like something like in millions. It's not a problem. You don't need to answer the exact figures. Anyone can speak. Hello. Am I audible?
Yes, sir, you are audible.
See, the cell count or gate, cell count in the sense, consider a simple AND gate or OR gate. That is a logic cell, right, in our design, and in some part of the design. So and this will be instantiated further multiple times, and these accounts to some n million number of cells. And what DFT pattern does is, each and every node. Okay. See, consider a simple design like this. This is some part of the hierarchy. Consider there is a flop here, and there will be some combi logic here. And in between, within this combi logic, there will be some n number of gates, like OR gate or AND gate. Consider a simple AND gate like this in some part of the design, or OR gate. What pattern does is, what pattern does is, it will help in detecting the manufacturing fault present on each node, like the input node and the output node. Okay, this is what actually the manufacturing, I mean the DFT pattern, or the test vector, what we call it as, a collection of test vector is called a pattern actually. So this is what pattern actually does. So the pattern which we give out during the tape out or during the handoff, we call the entire RTL to GDS process. This pattern will be delivered to ATE people, and ATE will test our design in order to test the manufacturing defect for present on each node. See, consider this gate is built some n number of transistors on the silicon, and on the each input node, there might be a chance of having a manufacturing defect, something like this. See, consider these are two wires here. Suppose this is an AND gate. See, where can I find an answer? Okay. See, consider there is an O. Okay, this was being removed. Huh? Okay. Okay, let me draw here. See, consider this is a simple AND gate, and you might face a fault here, like there is an open due to some incorrect fabrication process. So basically, manufacturing defects are present due to some factors like improper lithography or improper etching process, or what we call bad ion implementation. These are some of the factors that affects the manufacturing defects that eventually cause the silicon to fall under manufacturing defect category. So if there is an open, so what do you expect the response? So suppose if I give you 1, if I give you 0, what would be the expected response? It was 0. Expected response will be 0. In terms of AND gate functionality, am I correct? Hello? Hello?
Yes, sir. Yes, sir.
Yes, in terms of in terms of functionality, the expected response should be 0. But due to this manufacturing defect present on the net A, consider that is a net A. Hello, I just rejoined. Hello, am I audible?
Yes, sir, you are audible, sir.
Hello.
You are audible, sir.
Hello.
Hari, sir, you are audible, sir.
Okay, thanks. Okay, I think I have lost the connection in some part of the explanation. Can you please help me where did it get to?
Please share your screen, sir.
Oh, sorry.
When input of AND gate is open, what
Yes,
happens?
Okay. See, so it is open, right? So this is 2 criteria. One is the open defect. One is an open type of defect, and the another is a short circuit defect. So in order to identify these defects with a human eye, it is very much impossible task. But what we do is we give the pattern, and it helps to identify these actual defects present on the silicon. See, consider a 3 nanometer or 5 nanometer something like design. So if you see it from the outside atmosphere, you can't see the inner nets and tracks, right? Am I correct or not? Hello? Correct. Correct. So in order to identify, or in order to see these defects, it is a very difficult or tedious task. But what pattern does is it simply gives out the results like this in the form of locations. Sorry, it is too much big. We call it as failure locations in terms of ATE testing aspect. So what ATE people does is see, there are consider a pattern consists of n number of test vectors. I will just show you an example how the pattern looks like. Let us consider some 4 cycles, something like this. This is how the pattern will be converted when it goes to ATE people. So we do give the pattern in the form of a complete test vector, but this is not a test vector. This is simply a simplified format of test vector. A test vector will be something like this again. Let me draw here. A test vector, something looks like this. In between the flower brackets, there will be some responses stored like this, and so on, something like this. So this is how a test vector looks like. I do have access to show that, but I don't know whether it is being recorded. I can show my work area. Just give me a minute. I will share my work area. Venkateshwar, is this a session being recorded from your end?
Yes, sir, it is recorded.
It is recorded. Okay. Can you pause for a while, because I want to show my work area. How does the actual pattern look like?
Okay, sir. I will trim it later, sir.
You will terminate. Sorry, I can't hear you.
I will trim it later, sir. Can I trim it later?
Okay, okay. You can trim it. My personal PC was not responding at this time. But let me ask one thing. Any of you audience are aware of this pattern? How does the actual pattern look like? Not an issue, but see, let me tell you. So this is an actual input and output response. It is a collection of input and output response. Don't think this will be as simple as this. It will be a collection of many ones and zeros and many x. X tends to here x tends to not a valid input. That is why it is x. You can eliminate it. You can eliminate this x in the test vector by using some commands during your implementation. But there still exists some x and x. I mean the unknown state here in the pattern. C tends to clock where H are low, as you expected. Higher low.
Excuse me, sir.
Yes.
Sir, excuse me.
Yes.
If it is possible to show me practically, I will stop record, and after that I will start record, sir.
Okay. Then I will. Meanwhile, I will turn on my system. Till then, we can continue this. I was just trying to turn on my
Okay,
system. It was hacked.
Okay, sir.
It was right beside me.
Okay.
I don't know why it is getting turned off. By end of this session, I will definitely show you. Trust me. I have some images. Just okay. Where did I stop? Okay. So HRL will be tends to high and low. I mean 1 and 0. The actual response on the scan output. So what the actual testing criteria will be like this, something like this. They don't observe each and every response within the design. Instead, they will check the overall output on the scan out pin. Consider there is a die like this. Consider there is a die. There will be traditional methodology like checkerboard or something like that on the ATE. This is how a test plan looks like for digital testing. There will be some n number of in and out pins. What ATE does is they will first program the IOs. You will be having pads. Are you people aware of this pad? The power pad and something like this. I think in the previous session, they might have discussed about the pads, the physical design or physical verification. Any of the audience?
Yes, sir.
There will be the IO models outside our design, pad IOs. So instead of and each in-out pin will be connected to the pad output. The IO, we call it as IO ring. So what ATE people does is they program this IO before implementing the ATE test. So what sequence they give is this, what we have talked about, the ones and zeros. They will be giving this sequence right from the start to end. So consider there are sequence of ones and zeros like this in our test vector or pattern we call it as. There are some n number of test vectors. Each text vector, in order to test each vector, we require one clock cycle. That is C. So for each and every one clock cycle, they will measure the output on the other end. The scan out, we call it a scan out pin. Provided they should provide clock signal, reset signal, and other VDD, VSS which are needed for these pads to activate. And there will be input, scan input as well. Just I have mentioned in this slide. Where is it? There were some. These are the pins which I am talking about. So these will be a combination of ones and zeros in the form of test vector. Sorry. What ATE people actually do is they provide this sequence in a format called .pat file. Remember this word. There will be a .pat file. PAT file. Okay, this is the .pat file. Consider there will be some dummy cycles in the start, which helps for initialization. And later actual test gets started. Okay, consider like this, there will be some dummy cycles at the start. For initialization, we call it as initialization process, and later the actual test starts from the one definite cycle. Actually, ATE doesn't consider these cycles for actual test. What we have, we call it as dummy cycles. They will account for a process called initialization, and they will reset the entire circuit, entire design, or what we call it as wafer, or all the dice are present on the wafer. They will just reset using these dummy cycles, and then they will provide the actual sequence like this. It will be in the format like this, ones and zeros. Where was it? This is the format. Consider there are number of one to some. One is our start cycle. And so let us consider about 10,000 cycles. That will be 10,000 cycles will be n cycle. So they test all these cycles, and each and every cycle, as I said earlier, there will be there should need a one clock signal, one clock pulse, one complete clock pulse. This is the C. Each and every test vector will have a clock signal like this C. This clock signal will be supplied right away here using the IO. Okay. And I have one more image to show. And after rigorous testing or a repeated test, the AT will give out the results. If there exists any failures like this, I will just write down here. Failing locations on silicon. Based on the frequencies. Okay. And other criteria is if the failing locations are similar with respect to all the frequencies, then we can assume that there is a definite failure. There is a definite or real failure on the silicon. So the purpose of AT people testing at different frequencies is in order to differentiate the failures are real or not. See, as I said earlier, you might see the failing difference in the failure location based on the frequencies, and they will go down starting from 40 ns to right from 40 ns to they grow to even 1 megahertz as well. In my cases, it is like 1000 ns. Am I correct? 1000 ns is like 1 megahertz, correct? They will go beyond 1000. At least is the 1000 megahertz. They will test it in between this range when it comes to stuck test. They will measure the failing severity. I think, am I audible, right? Hello?
Yes, sir, you are audible.
Yes, okay. See, they will test at different frequencies and they will note down the failing locations, just like this in the image. In this image, you can see these failure locations belongs to one particular frequencies, but these failing locations will vary based upon the frequencies again. So that is why that is how the ATA testing takes place. If and another criteria is if the failing locations are similar. If the failing location count. Sorry, this is a count. The count is similar with respect to all the frequencies, whether it is tested at 40 ns or at 1 megahertz. If the failing count location is finite, I mean a unique number like something like 23 or 34, we can say there is a definite failure present on the silicon, and it can't be escaped by fine tuning the frequency. You can justify that there is a definite failure on silicon with respect to every frequency, and it can't be escaped by fine tuning this frequency. I think I have drawn something here. Okay, this is how AT testing takes place. They will program the IO and each pad that was related to scan pins. Please remember, they will program only scan, JTAG, and other VDD, VSS, the power pins, and the rest of them will be inactive because they can't consume more power while testing, so that they can't accommodate more number of pins during the test. For AT test, they will be having a separate thing called AT, we call it as AT test program. So before, I think someone has asked regarding this AT test program, testing procedure. For that matter, so I was explaining this thing. So before the testing takes place, ATA test engineers will have a program. We called it as ATE test program. And the people, what they do is, if the design is tested for the manufacturing defects, to identify the manufacturing defects, they will program only certain pins like scan, JTAG, or VDD, VSS, and the rest of the pins will be inactive during this test. The pins from analog or something kind of that, they will be inactive because they can't afford more. They can't overload the test program with unnecessary pins. So that is how the testing program takes place. And during the testing program, there will be a mandatory protocol, like they should consider the chip specification. So in the traditional RTL to GDS flow, the basic step, we call it as chip specification right from the start. So usually engineers do specify some parameters where at what temperature conditions or what clock frequencies the design need to be tested. They will all parameters will be included in the test program. Okay. This is regarding the ATE test. I think we can go to slides if I miss anything. Okay. Okay. We talked about basics. We should talk about scan as well. Let us go to scan.
Thank you, sir. I could understand the testing process, whatever you said. And even the previous one also, process you said, no? Due to network issue, I couldn't immediately respond at that time.
Okay, ma'am. I think you are aware of this testing right now. Okay.
Yeah.
So we engineers who are based in India are unfamiliar with the ATE testing, most of the people. So they might there won't be any getting of chance like that working with ATE people who are based in other countries. We don't actually have a facility to visit also. And very soon we might get this facility here in India, I hope. I think there were discussions in the government regarding the proposal of foundries in our country. Then we can see. Okay, next let's go to scan. Scan. Okay, I think I have started something about scan. So these are some of the inputs which are essential for scan implementation. These are the inputs. So sorry, these are the inputs, and I will describe one brief criteria regarding every implementation in DFT. Let me do that. So every implementation will be done in 3 phases. Will be done in, sorry, not 3, certain, let us consider a certain phase. We will name one by one based upon my discussion. First is our setup. We do enter in setup mode. This is right after initiating the licenses. Okay. This will not be included in phase. I mean the implementation phase. EDA2 license. We should please remember this criteria will be same for every DFT technique implementation, which I was going to discuss in further here in further. First we enter in setup mode and then we read the inputs. And next, if the setup mode gets passed in the sense if there is any kind of elaboration errors, we might end up in setup mode. Just as I said earlier, if there are any errors, we might end up in setup mode. if the setup mode gets passed in the sense it should satisfy, I mean, every input should be valid, and every input that was read by the tool should be valid. Next is the analysis mode. This is crucial. What EDA tool does is it analyzes the overall design and checks for design rule checks. So in the analysis mode, please remember, this is common for every implementation technique, whether you take it as CAN, EDT, ATPG, MBIST, any kind of DFT technique. This is the criteria. First, we need to initiate the tool licenses. So it depends upon the different DFT user. Whether there is a Tessent tool or Cadence or a Synopsys tool, we need to initiate the tool license and we need to enter the setup mode. And we have certain commands which can't be explained here in the session. Excuse, but see, there are some set of commands for every tool licenses and every implementation flow. I mean, whether it is CAN or ATPG, MBIST, or even LEC, any kind of thing. There will be some there is a set of certain commands. We call it as tool commands. These commands are different for different tool vendors. When it comes to Tessent, it will start something like set underscore, set context, something like this, set current design. To my knowledge, these are some of the commands initially we give. I'll just explain in simple. If you are about to start the implementation with the RTL based, we give it as RTL, DFT-RTL. If you are going to start with the netlist based, DFT-no RTL. We do start our implementation like this, and then we enter the setup mode. And during the setup mode, as I said, we read inputs. If there is a netlist, we use the command called verilog. If there is a library, we use it as read library. If there is any ECL related file, I mean, as I said earlier, there is tool connected information which was further it was implemented on beforehand during the implementation. We have some comment like this: code descriptions, read code descriptions. These are certain commands which are used in setup mode, and then analysis mode. If the setup mode gets passed, the tool automatically infers this analysis mode in action in the session, in the tool session. You could see if anything goes wrong here, the tool ends up like this. Sorry. The tool session throws like this. So I was in setup mode, and there will be an error statement about the session lengths. See, please do always remember, this is a basic fundamental thing which I was going to tell. See, if anything goes wrong during our implementation, try to read that error properly. The basic thing engineers do is they do not read the error statements completely. They will just tell the senior engineers, Hari, there is an error here. I ended up like this. There was an error statement, and I was unable to move further. So what I recommend is try to read that error. See, if there exists an elaboration error, try to recollect the code. See, just open the Verilog code. There is a feasibility from the tool, and it throws the error like this. There is an error in particular line, something like this, line 1, 2, 3, and it says like XYZ underscore 1, 2, 3 is not not a port, something like this, and not a part of hierarchy, something like ABCD, let us say ABCD, SCR, something like a hierarchy name. So what tool does, what tool is saying, it has found an error in line 123. What it says is there is a port called XYZ underscore 123 in the line number 123, and it does not belongs to this hierarchy. So how do you recollect from the basic fundamentals of Verilog? See, there is a port belongs to this hierarchy XYZ 123, but what tool says is it is not a port and it is not a part of hierarchy. That means this module got defined in somewhere of the Verilog code, and this was not a defined port in this module instantiation. See, when you go to Verilog code, we will end up like this. Am I correct? Module, we say it as ABCD SWER. We define ports. Consider this is an example. There is a port called XY123, and there is a Z. Should be comma. And later you define input output, something like this. So if you forgot to define this port in any of the input or output, the tool throws error like this. So that is where an elaboration error takes place. Okay, did you get this point? Hello.
Yes, sir.
Yes. See, this is a basic Verilog code, not proper. I haven't implemented the instantiation of anything like that. Just consider an example. There is a port called, see, this is an example for an error in setup. So suppose an engineer is going to implement a scan technique, and he has read all the inputs, and he has ended up in facing this error statement in the setup mode itself. So then what an engineer needs to do is you should read the error statement properly. You in line 123 of something like this will be given. In 123 in the file, there will be some directory pointing out some directory of file netlist.v. Suppose say netlist.v. So in netlist.v, there is a file called netlist.v. In the line 123 of line netlist 123, there is an elaboration error found by the tool. So what you needs to do is you should go through the Verilog code and see what all missing in the code. I mean, whether it was a definition or a port definition or instantiation, something like that, or even a single. Since Verilog language is case sensitive, even single alphabet can change the entire Verilog code. It ends up in error like this. Instead of XYZ, there is an XSZ. There will it's a bug. Okay. These are some of the kinds of errors we face in setup mode. That is what I was trying to tell. There will be some bugs in the inputs while implementing some sort of technique, whether it is scan, embed, or something. We will end up in setup mode like this. So if the inputs are proper, we will move to analysis mode. The tool automatically moves to analysis mode. And what tool does is it analyzes overall design and checks for design rule check connectivity. What tool does is it performs all these DRC checks, whatever we have mentioned earlier in this slide. It performs all these DRC checks. If something goes wrong, we need to analyze the design. There will be in the analysis mode, we have this feasibility. We will have some feasibility to view the design. Okay. Okay. So in order to fix the DRCs, In order to fix the DRCs, there will be set of tool recommendations. You can go through test and documentation if you are familiar with the test and documentation. I don't know, many of you don't have an access to test and documentation. If there exists any tool licenses from your organization or something, institution, something like that. May I know if any one of you people here in this meet have an access to test and tool documentation or working on VLSI design projects right now? I think most of the people are initialized with doctorates here in this meet. I think during their PhD
Sir,
or something.
we have access of cadence tools, sir, in our college.
Cadence tool, okay, ma'am.
Yes.
Then did you find any documentation, ma'am, in your root directory?
Root directory.
Okay.
Some manuals, sir. They'll give some
Yes, yes.
handouts.
See,
Yeah.
there will
Yes,
be
sir.
a user. There will be user manual.
Yeah. Yes, sir. Manuals, user manual.
Yes. Yeah, this is a basic fundamental where everyone should read. And another, and there will be another manual as well. Do you have any idea? Apart from user manual. Okay, see, user manual basically consists of, this will be in the root directory. Suppose if the root directory is like this, root tools, there will be tools inside the root directory if I'm not wrong. Here in the tools directory, there will be some categories like mentor. You can find, ma'am, if you have an access to tool licenses now itself, you can see inside the directory, there will be like this doc, user docs. This will be the path. I was not sure. It will differ from one tool to another. Inside the docs, there will be a user manual.pdf. Okay, so you can find the manuals in order to know how could we fix the DRCs. See, for every DRC, in order to fix every DRC, there will be tool recommended commands. And when coming to DRC, I should tell you this: DRCs are classified into 3 types. One is severe, one is warning, one is note. Okay, these are different kinds of different types of these are subclasses for DRCs. See, if there is a severity in the DRC, suppose as I said earlier, there is one kind of DRC like DFT-C6 or something. It's DFT-C6 C1. Let us consider there is a DRC. Consider C6. See, basically in C6, what C6 does is it's a clock data trace violation in test. During you might face this DRC during scan and ATPG as well. Scan or ATPG. If you don't, if there exists a violation, real violation C6. See, this is an example. Don't think there is a. This is only the big violation that Hari is telling. See, this is one example. There is a C6 violation. Why I do consider this C6 violation is this is basically a warning. Basically, by default, it is a warning. Okay, this is not. Sorry, I said it is severe. Sorry, it was an error. Sorry, DRCs are 3 types. Basically, it was one is error, another is warning, another is note. You can ignore note. See, you can always ignore note. Please do note. A note is a type of DRC, one such DRC you can ignore. And later you can examine. You can ignore But when it comes to error and warning, you have to be very careful. You should definitely fix this error. Okay. Warning sometimes warning may not be severe. If you think if the warning if you think this DRC warning kind of DRC will affect your implementation, then you can treat it as error. So in Descent, there is a feasibility to change the severity of a DRC. See, there is a command called set DRC handling, where you can turn the DRC into warning. Sorry, this is an error basically, as I mentioned. You can change the severity of a DRC into another type like this. This is in terms of Descent. Set DRC handling is a command. Yes, small. See, basically, what I was trying to explain is in the analysis mode, we might face DRCs. We will definitely face the DRCs without any fixes. See, basically, every implementation technique that was followed in the VLSI design flow is like a trial and error method. See, we are not sure about the design until and unless we read the design, we examine the design, and we can't anticipate the DRCs or failures on the forefront. Am I correct? Hello? Hello?
Yes, sir.
Please do respond. Yes. See, it's a kind of trial and error method. Whatever we do in the entire VLSI design flow, right from the validation, even if you think of design verification team, they do write some test bench code for the Verilog code which were developed by ATAL team. So they can't every engineer or every person, with irrespective of any part of the VLSI design flow, right from the RTL to JDS, may not guarantee that every iteration will pass in the first attempt. They might take some days or hours of time in order to check, in order to double check or cross check whatever the code they have wrote. So that is how it is. When it comes to DFD, there is no necessity of in-depth knowledge of Verilog coding. I suggest if a person here in the audience, if any one of you are interested in going to DFD domain and in nearby future, I recommend there is a necessity of Verilog code up to some extent. You should learn Verilog coding in order to identify those bugs, what I have mentioned earlier in the setup mode. See, there could be some elaboration errors because we can't be sure that every input we consider during our implementation is correct. See, we should have a capability when you start the implementation. The engineer should have a capability in order to judge that error, and we should recommend the RTL team. See, this is whatever the files you have provided. There is a bug in this particular file, and this is the fix, and I have made from my end, and I have moved further. See, every engineer, experienced engineer, like 2 to 3 years experience, minimum of 2 to 3 in the industry, should have this capability fixing the minute errors like this on their own. Because you can't wait or you can't email the RTL team every time and every minute. See, there is an error, you should update the file and give me. Because one thing that matters is, in the end of the day, one thing that matters is runtime. Runtime is very crucial in order to see entire RTL to GTS flow depends upon this one factor, runtime. Because when you consider a minimal runtime, you can tape out by the estimated date. Correct. So this is one such factor. What client expects from the service companies or any other engineers based in any part of the company. So runtime is one such crucial factor. And another thing, where have I left? So the ability to find the errors and fix by ourselves is one such ability. So if you are planning to go to DFT domain in future, you should have some learnings on Verilog and system and any one of the language, hardware description language, Verilog or system Verilog code. And when coming to this DRCs, so analysis mode is all about DRCs. There will be nothing else from my perspective. Major task is to fix the DRCs. Okay. And another thing is insertion. These are the main three items. One is analysis, one is setup mode, one is analysis mode, one is insertion mode. So insertion mode, sorry. So the third one is the insertion mode. This is optional. Why it is optional, I will explain. See, the name itself in the DFT, we do consider as design for test. This means we insert extra design means okay. This is our basic funda for the DFT. So whenever we say we insert or we add, that comes under insertion mode. So whenever a engineer, DFT engineer tries to add some extra logic in the current design or the actual design, we should insert. So we should enter into setup mode. Let us say there is a command call in the Tessent, whatever I use. I was more familiar with the Tessent tool. I use Tessent tool for the overall implementation. Set system mode. There is a command called set system mode. We can so this is the kind of command we give when a user needs to enter into insertion mode. In place of insertion, we can give an insertion. Other terms setup. This is valid. Another one is analysis. This is valid. So any other terminology, if you try to give, the tool throws an error. So that is how the case sensitivity will be when dealing with EDA tools. Okay. So what I was trying to explain is the basic steps are like this. First, you need to initiate the EDA tool license depending upon the availability, and you should use some tool commands in order to start your implementation. The first and foremost step is the setup mode, where you read the inputs. If there exists any error, as I explained, you should fix, or you should ask the RTL engineer. You can report the RTL engineer. See, some files are missing in the given IP directory or something like that. Or in this particular RTL file, there is no such module what you have defined later on in the Verilog code. So you should, this is my error statement. You can send the screen snip of the error statement to the RTL engineer so that they will understand and they can retrieve the code and they can give you back after fixing it. So when the setup is clear, I mean the inputs are proper, this is the main task what DFT engineer actually does. See, improper fixing of DRCs will lead to Add implementation. See, you should not. Please remember, since most of audience are I think some of you are completed a doctorate or something like that. So PhD candidates, maybe this will be helpful for your. I mean, there will be something like that. What do we call for the PhD? In order to obtain the PhD, there should be something at the end of the course. There will be some project, live project, right? You will be doing some live projects. Am I correct? Ma'am, you have
Yes, sir.
licenses. You have the licenses to implement Leela ma'am. I think she's Leela ma'am. Ma'am,
Yes, sir. Yes, sir.
Yes, yes. Are you pursuing your PhD?
Yeah, I have completed, sir. I have completed my
Okay,
PhD.
great. You have completed. I think you
Yeah.
might be aware of handling these tools and implementing one live project during your PhD.
Yeah. Yes, sir. Yes, sir.
Yes, yes.
Yes,
So,
I have used
see,
Cadence, some of the tools, sir,
okay,
like
great.
Virtuoso and all some digital tools I have
Okay.
made use
So,
during
ma'am,
my PhD.
I just want to ask and let other audience know, have you went through any of these? So what is the, sorry, before asking this, what is our main platform? Like, have you worked on RTL and validation or
Uh,
something like design verification?
yes, sir. Yes, sir. I worked on RTL, sir.
RTL, because many
Yeah.
people might not get the chance to implement or consider DFT as a main topic in their PhD program.
Yeah. So mine
Yes.
is not DFT, sir. I have used, I'm in RTL, sir.
Okay.
RTL
So,
and then till synthesis I did, and some part even I have used Virtuoso also. Some circuit simulations also I have made use. So I used a Virtuoso tool also during that time.
I think you might not hear heard about DRCs during implementation, but theoretically you might heard that the term called DRC, right?
Yeah. Yes, sir.
Design
Yes,
rule
sir.
check.
Yeah.
During
Design
your
rule checks.
implementation, yes, okay. But during your
Yeah.
implementation, whatever you have said, you have worked on RTL, but you might not face DRCs. But you might end up in facing bugs, like there will be some elaboration errors, such thing, right?
Yeah. Yes, sir. Yes, sir.
Okay. And another thing, ma'am, I just want to know. So, is there
DRC
any
checks
scope?
actually, I could see when we have, during the tool training procedure, we did till from RTL to GDS too, sir. During that
Okay.
process, we have designed even the layout also. When the company people came for training to give some training to us, so even we did the layout designs also. So during that process, we have seen that DRC checks during the layout designs actually.
Okay, actually,
Design
okay.
rule checks.
Yes, DRCs will be a part of physical verification as well, because
Yeah.
PD will also face terminology because they do check for DRCs.
Yeah.
They do PV person will do some geometrical checks, if I'm not wrong. They will compare LVS to schematic.
Yes, sir.
What we
That
call
also
as
I have used. We have used
yes.
LVS
Yes,
to schematic.
but
Yes.
but here in terms of DFT, what I was going to explain is the tool, whatever be the vendor, whether it is Tessent, Cadence, or Synopsys tool, what tool does is it checks all these categories. See, this category will covers all the entire design criteria. If there is, let me explain in
Okay.
short. If there exists any RAM in your design, this A rules concentrates on those particular RAMs. Okay, if there exists no RAM in your design, there is no chance of
Sir, your voice is not audible, sir.
Sir, your mic is muted.
All the participants, there is some network issue with our speaker. He will join within a minute. Please wait.
Hi, hi. Hello.
Harigar, you are
Hello?
audible now. Yes, sir. Harigar.
Sorry, it's just a power. It's a power up. It's a power cut here at my location, so it just got interrupted. So we were discussing something regarding DRCs, right? Okay. Okay, I'll just
Yes, sir.
fulfill. Yeah, I'll just try to fulfill my presentation. So see, this is the basic criteria where every engineer does in the industry. Right from the sorry, this is the see, this is a implementation flow. This is how it follows. Just separate. Actually, it ends up in the analysis mode only. But if there exists a need in the design connectivity, or if the DFT user is trying to add some extra design or bypass the logic of the existing design, we need to enter in this insertion. So insertion is all about adding the extra design. In the design related command, there is a command called intercept connection. See, for suppose I will explain in brief here in the. My screen is visible, right? Okay, my screen. I was sharing.
Yes,
See,
sir. It is.
suppose this is a design. Assume this is a clock reset control network. This is the one. Every design has this one particular hierarchy. This is common in every designs which I have worked on. We call it as clock reset control. What designer does is it takes a common clock input of 1 ns, and then he adds the clock dividers inside it. It is right here. This is the clock reset control. So there will be certain dividers inside it. It helps to divide further more frequencies, smaller frequencies. If suppose if it is 1 ns, if you can divide it by 2, we get as 500 here as output of this clock divider 1. This is 500. This is 500 certain will be further divided by 2. That will be 250. And this and so on. Every output on the clock divider will be an overall output, each individual overall output of certain frequencies. These certain frequencies based upon the chip specification will be connected to different hierarchies like this. Suppose this is one hierarchy, this is one hierarchy, this is one hierarchy. The connection formation will be like this. See, like this. See, depending upon chip specification, there will be certain module codes which gets instantiated within the entire design. And what RTL engineers does is they will have a clock reset control here in the design, like this, where they take a common clock input from the overall output, sorry, overall input, and it is further divided into further more frequencies, like smaller frequencies like 500, 125, 200, something like that. And each frequency output will be further transmitted to different hierarchies based on the chip specification. If each module has its own functionality, don't think every module has same functionality, because there will be a different frequency for different functionality based upon the chip specification, right? Okay. See, if something, let us assume there is a one clock, there is a clock output called as 1 kHz or 1 MHz. See, as I said earlier, this is the lowest frequency which DFT does not consider for test. What is the lowest frequency? It should be 40 ns. This is the slow clock frequency. or we call it as scan clock frequency. There will be a scan clock input on the top of your design. As I mentioned earlier here in this slide or in this lecture, we have a scan clock that will be the slow clock in our design. See here, it is 1 megahertz, it is very less than 40 ns. So what we do is we can bypass this clock by using a mux. Suppose you can have a mux. You can connect this to I0. Consider this is an I0. We can connect I1 to suitable clock frequencies like the scan clock. We will be having a separate hierarchy where all these scan pins get entered here. We can bring out this connection like this. Sorry, this is a scan clock, suitable clock. And the selector line, the scan mode. The reason behind connecting selective line to scan mode is the scan mode or test mode, we call it as in DFT, that will be always 1, high. Remember the scan mode or test mode, which we consider in DFT, we call it as test mode or scan mode. In order to test the design, see, why the scan mode being 1? The reason is, see, we have put one mux here in the design as an example. There will be n number of muxes in the design where they will be bypassing in this scenario. So what designer does is they will connect this selector line to scan mode. The I1 will be a suitable clock frequency which is available for DFT testing. I0 will be a random clock frequency which is used for functional test. Okay, that is why the reason every mux that is the reason behind the scan the selector line being connected to scan mode. I have mentioned here about the scan mode. This is one such DFT input pin which every designer, which every DFT engineer needs. These certain pins will be given by the RTL team itself. Before, see, if the design has a necessity of DFT, implementing DFT techniques, they have to compromise on these pins. They should allocate some n number of pins depending upon the complexity of the design. Always these will be standard, and these scan in and scan out will be varied depending upon the design cell count. If the design is big, we will be having 3 extra pins in order to accommodate these pins into EDT techniques, where we have EDT. I will have a new slide here. So the EDT will look like this. See, why the necessity of the scan pins, necessity of extra scan pins is like this. If there are 3 pins, our design count is somewhat like 1 million or something like that. And you have some n number of scan chains. Suppose consider there are 100 scan chains. Think on a note, you are having 100 scan chains, but you are having 1 scan in and 1 scan out. Just try to assume that you are implementing an EDT technique with 100 scan chains with 1 scan in and 1 scan out on either ends of the DFT. This is the EDT instrument. Actually, this does not resemble the actual design. It is just a block diagram. What I was trying to explain is when you implement a DFT, there will be a formation of certain scan chains in the design. These scan chains are basically clock based. Depending upon the clock domain, the tool stitches each individual cells into separate chains. Okay. See, for example, there are 100 scan chains and one single scan in and one single scan out. There will be more tester cycles and more test data volume in terms of pattern. This is in terms of pattern. Test data volume in terms of pattern. The more test data volume and the more number of pattern tends to more ATE test time. When implementing EDT with one scan in and one scan out. And in another way, if you could accommodate 3 pins on either ends, the compression ratio will be 3x. Tends to low number of test cycles and less test data volume, and hence less tester time. See, the main goal behind implementing EDT in the real-time DFT implementation technique is in order to compress the test logic and make the circuit testable within the less time. I mean to say is ATE people can use the can have a less runtime while testing the DFT pattern. That is what I was trying to say. Next, come to implementation. Okay, I forgot about the BIST. Okay, so I will just give a glance about BIST. Scan is completed. Okay, so I have to say one more thing regarding scan. So what scan does is, see, basically without scan implementation, there will be some set of flops. We have different flops. Theoretically, we call as JK flip-flop or something like that, data D flip-flop. When it comes to scan, the difference between a scan flop and a non-scan flop, I mean the normal D flip-flop and a scan flop is like this. Just give me a minute. I will just use the flop. There will be SI, scan input, SC, data, clock, reset. When it comes to normal flip-flop, you might see only 3 pins. Sorry, Q, I missed out Q. Set D, clock, reset, Q. This is a normal flop. This is the scan flop. This is the basic difference between the scan flop and the normal D flip-flop. So until and unless, and one more thing is, by default, there will be some scannable flops inside the design, whether you perform scan insertion or not. What I mean to say is, the RTL team directly inserts a scannable kind of flop. They will be including a scannable kind of flop inside the design by default itself. And after scan insertion, and every D flip-flop will be turned out into scan flip-flop, and every flop will have a controllability in terms of DFT. See, these 2 pins comes under DFT pins. These 2 pins will take control of your entire design. In between the flops, there will be a combi logic like this. And each scan flop I will go for another slide. Consider this is how a design looks like when you open in a visualizer using a EDA tool. See, this is a flop 1. This is a flop 2. This is a flop 3. See, every flop will be interconnected like this. This will be our scan in, and the end of the flop of each scan chain will be connected to scan out. The operation in between these scan chain will be checked by SI to SO. Whether the chain is connected properly or not, we can perform the chain test, the scan chain test, we call it as in DFT. It will make sure that every scan flop is interconnected and it is stitched properly. For in order to test this scan chain, we will enable the scan enable. It will be high. When scan enable high, the operation takes place like this: SI to Q. When scan enable low, it tests for capture operation. I mean the D to Q. This is how this is a sample, an example for how an operation look like in terms of DFT. There will be a combi logic in between the flops, and we DFT people will take care of these scannable flops. We don't bother about the combi logic present inside between these flops, because the main motive is to we need to attain the controllability and observability of the overall design. That is why we add these pins in order to make the test circuit more testable. When it comes to BIST, I think we are running out of time. So BIST is there is two kinds of BIST. We call it as logic BIST and memory BIST. Please remember, logic test is different from logic BIST. This is entirely different. Okay. See, when it comes to memory BIST, if there exists any memories in the design, the tool performs these kinds of DRCs. It performs BIST rules and A rules as well. Even RAM comes under memory. If there is a time, we can extend for 10 more minutes. So now I can draw the block diagram for memory BIST. See, I think I have the PPT. Wait. Okay. So there is no proper block diagram, but there will be three main topics when it comes to BIST architecture. The BIST architecture itself consists of random test pattern generator, where you can have a separate pattern to test the memories in the design. When it comes to pattern check, as I talked about earlier, there will be this pattern. What we have talked about is scan pattern. Let us say pattern is of two types: sorry, 3 types. Pattern differs. Just stuck it at speed. So using the ATPG technique, we do generate the patterns. If the user needs to test the pattern, if the user needs to generate the pattern, by default, the tool will automatically generate the stuck pattern. If the user needs to test it at speed, at speed pattern, you should use the certain command in the test provided tool. We have some command like set code description, like set current mode. We will be having some tool related commands to turn off that speed. Similarly, for MBIST, we will be having pattern spec. Please remember, to generate the MBIST pattern, we don't use the ATPG technique. We use a separate criteria called pattern specification. ATPG tool only do generate the scan pattern itself, but not the MBIST. Please do remember. And for MBIST, the fault test will be based on default algorithm. So unlike a stuck and fault test, this algorithm has the capability different fault test. That is how MBIST works. BIST works. Logic based, to be honest, because we haven't implemented logic BIST. But in coming days, there will be a new. What I want to discuss is there will be new techniques. Right now, there were in implementation stage by most of the EDA. I mean the fabless companies like NVIDIA or something, AMD, something like that. There is a technique called SSN. This is the most advanced technique, and this was recently launched. It was launched earlier in earlier years, but it was came into light in recent days. It is a scan streaming network. This will be going to be a popular technique in coming days. And also the IST in system test. This is the old technique, but for every ADAS application chip, this is essential. Companies like Qualcomm will be using this in system test implementation. Just see, this is same as like scan. I mean, whatever you call implementation techniques in the DFT, in system test itself is implementation technique. And scan streams network is SSN. SSN is not an implementation technique, but it is an extra added design instrument. It's an extra added design instrument, just like EDT future. See, scan is an implementation technique, but EDT doesn't. See, EDT is an extra added feature. Without EDT also, we can fulfill the DFT implementation. Don't consider EDT is a completely a single level implementation. EDT is an extra feature, just like SSN. And boundary scan itself is implementation technique. Boundary scan is one such popular technique. These are some of the techniques that are currently in progress from DFT. Maybe I don't know this could be more popular in coming days, because scan is everyone aware. Sorry, this is the future, not the technique. Sorry, this could be the most popular feature in coming days for entire VLSI design flow, because it reduces. It has an impact on the PPA factor, especially the area factor. Instead of adding many other design instruments in the design, an SSN can replace that feature in coming days. I think I have discussed most of the topics here. I think how many are in the queue? It's like 25 people. Okay, everyone are still patient and listening. Okay, if you have audience, if you have any doubts or any queries, you can now shoot. Hello. If you need
Yes,
any
sir.
assistance or need any other topic which I have missed or which you want from my end, you can ask. Someone has responded as this. I think. Do you have any queries to ask? Please. Very nice session, very good information, but not up to the mark, Shamshan, because due to some extensive workload, I haven't prepared well, but I have tried my best. So what I have said till now is right from my heart. See, I have prepared the PPT, but I was not interested in explaining the PPT because most of you are in profession, right? See, if you are from the student category, I could have explained the PPT, but that doesn't work out for you people. So that is the reason I have correlated the DFT with the real-time applications. Okay, one more compliment. Okay, please, anyone, we can extend up to 9:15. I was free. There is a weekend for me. I can work, no problem. Thank you, sir. Welcome. Next. Please do ask if you have any queries. I was open now. We have time up to 9:15. There were 8 minutes more. I can ask them. Please,
Sir,
yes.
yeah, you said about like only if a single pin is available for scan, then more
Yes.
number of clock cycles we need to run, like that you said. Can you take an example of a larger design and a smaller design? Just can you differentiate in terms of how, I mean, number of clock cycles and all? If
It's
only a
not like
single scan.
it's not about clock cycles, Andy. See, what I was going to tell is the main concept is like compression. It's a matter of compression. The compressing the design in order to make it testable with the minimum data volume. See, consider a design with suppose we consider with smaller numbers, so smaller figures like 100 and 1000. Suppose there are 100 cells in a design. But in order to test each cell, there will be n number of vectors. For consider, let us say for a design with 100 cell count, there are 1000 number of vectors. Okay, and when it comes to design with another one is 1000, right? Sorry, I was getting confused with figures. I will just present here. Okay, it will be very. See, the main motive of EDT is minimum data volume. I will correlate each and every terminology here. Please wait. Minimum data volume within minimum tester time. Okay. So here test data volume in the sense for test vectors. Okay, when does the test vectors gets decreased? As I said earlier, the fault detection happens on each and every node. Consider there are 100 cells. Suppose say there will be no design in the world with 100 cells. Just consider it as an example. 100 cells. For 100 cells, sorry, for 100 cells, the test vector count is 1K. Let us consider. For 1000 cells, the test vector count is 10K. Okay. So in the basic idea is the basic outcome will be like this. In order to test the 1K vectors, the pattern volume will be 1 MB. Consider as 1 MB in the .zz format. Actually, the format will be in the compressed format. The pattern will be of compressed format every time when generated by the ATPG2 with no EDT. Okay, there will be no EDT here. Consider. Okay, for the 10K vector count, let us say after compressing, let us suppose say this was 5 MB only after ZZ format with no EDT. From here, we can say the tester time will be, consider say it is 1 hour. Tester time 5 hours. Let us suppose say. So on what cell count would you implement EDT now? Suppose if you could implement on a design like 100,000 cells, the same criteria when implied with EDT, what happens is the test vector count decreases. To understand this, you need to go through the EDT manual. Actually, I was just saying orally, but why, sir, why the test vector count increases? If the question is from your end, you should definitely find the answer from the textbook. The test vector count will be minimal compared to no EDT. And so will be the less tested time. So the main agenda of EDT is to provide the overall design information in terms of patterns. So the overall output from the DFT end will be the pattern only, not the design. So the design will be already supplied through layout from the GDS team. What we call GDS will be supplied to Foundry in order to proceed for fabrication. The only agenda, the only output from the DFT will be the pattern. See, when it comes to pattern and testing, whatever the pattern we give should be facilitated for ATA testing in such a way the pattern should account less data volume and less tester time to test the overall design. See the results here. It takes with EDT, it takes less than 5 hours. Not sure how many hours. It takes less than 5 hours with EDT, because the compression technique enables the test vectors into minimal chains, and the EDT. When it comes to EDT, I missed one point. Consider EDT with 2 scan in and scan outs. Okay, EDT with 2 scan in and scan outs, not with single EDT. See, with single EDT pin, if you do EDT or if you do not do EDT, it doesn't matter because it is single track as one SA to one S4. When it comes to two scan in and two scan outs, the data will be shared in between these two pins. Right from SA to S4, the test, what I mean to say is the data comparison will be checked simultaneously.
Okay, sir, I could understand.
Between
Yeah.
two scan-ins and two scan-outs.
Okay.
So that is how the compression technique works. But please understand the main agenda is to the DFT should provide a pattern or implement whatever the techniques, I mean the EDT techniques. It should be in such a way it should facilitate the tester. See, if the design count is too large, we can't do anything. It should take whether you have implemented a full level of EDT implementation. I mean to say, if you have considered all the available scan-in and scan-outs for the EDT, and still you are facing a more tester time, you should compromise on the test. There is no looking back. But when it comes to moderate designs, you should plan the EDT technique in such a way. You should give the see for moderate designs. Tester people usually don't spend lots of hours to test the design because they need to test millions of parts. Am I right? Millions, not thousands of parts. In order to test the die, and then they move to packaging, and again in the packaging also they will retest, and then they will transfer to actual vendor. This is how ATE works. So in order to minimize the test data volume and test time, we implement EDT. That is the main agenda for main reason for EDT to implement it. Any other questions? I think I have justified your question, ma'am, Leela.
Yes, sir. Yes, sir. Thank you, sir. Thank you for a good presentation. You have discussed all concepts almost from a real-time scenario. Thank you. That was really very helpful for us.
Yes.
Thank you, sir, once again.
Yes, because simply explaining the PPT will not do, because you people are aware of these textbooks, and right. So everything which was framed in the PPT will be in the textbook, because I can't explain many number of times the same matter. So I just thought of explaining in this way. I hope all have liked it.
Yes, sir. Yes, sir. Because whatever fault models
Okay.
and all you have in your PPT, we have all those in books in our
Yes,
curriculum
it will
also.
be in the
But
textbooks.
the concepts
Then,
you have
yes,
discussed
then-
are helpful. Really. Thank
yes,
you.
yes. Because yeah. So any other audience, any other from the audience would like to speak? You can unmute yourself and you can speak.
Thank you, Hari sir. The session was
You can call me
really
as
the session was really excellent, sir. Wonderful presentation. The topic was too good. Design for testability. It was highly informative and effectively addressed both theoretical as well as practical aspects of the topic, sir. You provided thorough explanation of the practical need for design and testability, supporting with real-time examples, making the concepts more relatable and easy to understand for everyone. The key
right, Venkatesh garu.
Yes, sir. Yes.
Okay. If you are planning to give out this session to others, you can trim some information before projecting.
What is
before
the
sharing.
information I have to do, sir?
Whatever the snips I have shared from my end, I can. So I have shared some work-related snips. You can ignore. You can snip. You can trim those.
Okay, sir. Sure, sir.
Okay, sir. We'll take care of that. Once the video is prepared, we will share that video to you. After your permission only, we'll release that video.
No, you can send to.
We'll keep it.
I think Venkatesh Garu has a contact with Dilip Garu. You can send to him.
Okay, sir. No
Okay.
problem.
Okay. And any
Thank
other?
you, sir.
Any
We
other?
would like to see you in your lectures in our future endeavors, sir. If participants have any queries, we will definitely mail to you, sir.
Okay, thank you. Okay, you guys can drop.
Dear participants,
Please.
we'll have a photo. All of you unmute your cameras. Hello, sir.
Right.
If you can also unmute your camera.
Camera on. Currently, there was no light on me. Even if I turn on the camera, you can't see.
Okay, sir. Okay.
Okay.